Hey everyone, and welcome. Today we're going to tackle a classic coding problem, the fractional knapsack. Now it might sound a little intimidating, but trust me, the solution is surprisingly elegant and really powerful. If you've got a coding interview on the horizon, this is definitely one you want in your toolkit.
So here's how we're going to break it down. We'll start with the basic problem, what I like to call the Packer's dilemma. Then we'll uncover the golden ratio that just cracks the whole thing wide open. After that, we'll dive into the greedy strategy, look at its code and complexity, and wrap up by comparing it to its trickier cousin, the 0-1 knapsack. Let's get into it.
All right, section 1. At its core, this whole thing is really just a problem of optimization. You know, how do you get the most bang for your buck when you've got a really strict limit?
So, think about this for a second. What if you could slice up items into perfect little pieces so your backpack always delivers the absolute maximum value? This right here, this question, it's the key that unlocks everything. See, in the real world, you either take the whole laptop or you leave it, right? But here, we have a kind of superpower, divisibility. And believe me, that changes the entire game.
Okay, so here's the formal definition. Imagine you've got a bunch of items. Each one has a value, you know, how much it's worth, and a weight. And you have a knapsack with a limited capacity. Your goal? To cram as much value as you can into that knapsack without it breaking. But, and this is the big but, you can slice and dice them. You can take just a tiny sliver of an item or the whole thing. That's the magic ingredient here.
So, the big question is, how do you decide what to take? Which items or which fractions of items should you grab first? Well, the solution lies in this one single beautiful metric that tells us exactly what to prioritize.
And this gold bar analogy, it is absolutely perfect. Seriously, just for a second, forget how big or valuable each bar is overall. If you could shave off pieces, you'd always go for the purest gold first, right? You want the most value packed into the smallest possible weight. And that's the exact same logic we're going to use here.
So that purity we were talking about, that's what we call value density. It's super simple. Just take the item's value and divide it by its weight. That's it. This ratio is the single most important piece of information in this whole problem. It's our North Star, our golden ratio, that's going to guide every single decision we make.
Okay, check this out, because this table shows a really common trap people fall into. Your eyes immediately go to item 3, right? It has the highest value, 120. But look closer, it's also the least dense. The real winner here, our most precious item, is actually item 1. Even though its value is only 60, its value density is a whopping 6.0. That's the one we want first. All right, so now that we have this idea of value density, let's build our strategy. We can actually outline a super simple greedy algorithm. And here's the best part. This isn't just a good guess or a close enough approach. This method is provably, mathematically, the optimal solution every time.
And it's so beautifully simple. Just 3 steps. Step 1, calculate the value density for every single item. Step 2, sort them all, from the highest density down to the lowest. And step 3, just go down that sorted list and start packing. Take the whole item if it fits. When you get to one that doesn't, just slice off exactly what you need to fill the bag perfectly. That's the whole thing.
Okay, let's make this real. We'll use our example items from before. Imagine our knapsack has a capacity of 50. So, following our sorted list, we grab the most dense item first. That's item 1. It weighs 10. Our capacity is 50, so yeah, that fits easy. We'll take the whole thing. Boom. We've added 60 to our total value. Okay, so we've used up 10 units of space, which means we now have 40 left.
Next up on our density sorted list is item 2. It weighs 20, we have 40 units of space left, so yeah, that fits no problem. Let's throw the whole thing in there. That's another 100 in value.
All right, bag's getting full. We're now down to just 20 units of capacity.
And now for the grand finale, the fractional part. The next item is item 3, which weighs 30. Uh-oh. We only have 20 units of space left. It's too big. But we can slice it. So we just take the 20 units of weight that we need. Since the item's total weight is 30, we're taking 20 out of 30, or 2/3 of the item. That means we also get 2/3 of its value, which is 80.
And just like that, our knapsack is filled to the absolute brim. The total value we've managed to pack is 60 plus 100 plus 80 for a grand total of 240. That's our maximum.
So you might be asking, how do we know for sure that 240 is the best we can do? Well, the proof is actually really intuitive. It's called the exchange argument. Just think about it.
If you had any other combination in your bag and it included even a tiny piece of a less dense item while you left behind a piece of a more dense one, you could always make a swap, right? You could trade that low-value piece for the high-value piece and your total value would go up. It's impossible to beat the greedy strategy because any other choice would be suboptimal.
Okay, theory is great, but let's talk practice. Let's talk performance, because in a coding interview, they're not just going to ask you for the idea. They'll want to know how efficient your solution is. Let's get into the code and complexity. So, when we talk about how fast this runs, the time complexity is O of n log n, and you might ask why. Well, it's pretty simple. The most work we do, the heaviest lifting, is sorting all the items by their density at the very beginning. After that, we're just zipping through the list once. And for space, we can be super efficient. If we do an in-place sort, we can solve this with O of 1 or constant extra space. Pretty neat.
Just to really hammer it home, calculating all those ratios, that's a linear O of n task. Sorting them, that's our bottleneck, O of n log n. And then walking through the list to fill the bag, that's another quick O of n pass. Since the sort is the slowest part, it's the part that defines our overall complexity. That's why we say the whole thing is O of n log n.
All right, last section, and this is a really important one. We need to clear up a super common point of confusion. You see, the fractional knapsack has a famous and much trickier relative, and it is vital that you know the difference between them, especially for an interview.
And this comparison really lays it all out. On the one hand, you have our fractional knapsack. Items can be split, and our simple, greedy, value density strategy is guaranteed to be optimal. Easy peasy. But on the other hand, you have the 0-1 knapsack. Here, items are indivisible. You take the whole thing or you take 0 of it. And that simple greedy strategy, it completely falls apart. It's just not optimal anymore. That problem is a whole different beast that usually needs something more powerful, like dynamic programming.
So there you have it. We've mastered the divisible. We've seen how that one simple rule, that you can slice up items, leads to this incredibly elegant and efficient greedy solution. But it leaves us with a really big question, doesn't it? What happens when that power is taken away? What do you do when the items can't be split and you're forced to make those all-or-nothing choices? Well, that's a story for another time.